Welcome to another deep dive. We're going to extract the signal from the noise today. I'm really looking forward to this one.
Yeah, should be interesting. Lots of fascinating new research out there to unpack, that's for sure.
Definitely. And we've got three very distinct, but I think equally mind-blowing areas we're going to zero in on today. So we've got some breakthroughs that are happening at the microscopic level, like almost too small to even fathom, but that could revolutionize artificial intelligence. And
Absolutely.
then we're going to zoom out to the edge of the observable universe.
As far out as we can see, literally.
Literally, yeah. And then kind of come back down to Earth.
Right. Back to our own backyard, so to speak.
Yeah. And look at some surprising new insights into, well, the biological roots of our own mental well-being.
I think that last one might surprise some people. It's not an area you typically associate with cutting-edge science.
Absolute. But that's what I love about these deep dives. It's like a curated tour of the most interesting, most mind-bending frontiers of science, right?
It really is, and what strikes me about the sources you've gathered today is how these seemingly totally unrelated fields are all offering these profound new perspectives on some really fundamental questions.
Yeah, I totally agree.
I mean, we're going to be talking about advancements in AI hardware, looking back billions of years to the dawn of galaxies, and then exploring this potentially game-changing understanding of how certain mental health conditions might originate.
Exactly. And our goal in this deep dive is to pull out the most significant insights from all of this research, make it accessible.
Right, like a Cliff's Notes version, but hopefully even more engaging.
Exactly. Give you that moment.
Yeah.
Help you understand the big picture without overwhelming you with too much technical stuff.
I like that.
So shall we jump into it?
Let's do it.
All right, so let's start with the first area, these new memristors that are making waves in the world of artificial intelligence. I have to admit, even I had to look up exactly what a memristor is when I first saw this paper.
Oh, absolutely. Not a term you hear every day. And even for those who are familiar, there's some really novel developments here that are worth digging into.
Okay, so before we get into the specifics, can you maybe give us a high-level explanation of what memristors are and why people are so excited about them?
Yeah, absolutely. So at the most basic level, memristors are these really interesting electrical components, and they offer this potential for much more energy efficient computing, which is a huge deal because right now our computers, especially the really powerful ones used in AI, they consume a massive amount of energy.
Right, we hear all the time about the giant data centers and how much electricity they use.
Exactly. But what makes memristors so intriguing is that they're not just about saving energy. They also have this really fascinating parallel to how neurons in our own brains function.
Okay, that's where it gets really interesting. So how do they actually mimic brain cells?
So think about it this way. A traditional computer uses transistors, which are basically like switches that turn on or off to represent ones and zeros, the binary language of computers. But neurons in our brains, they don't just have these two states. They can exist in this whole spectrum of states, and their connections can strengthen or weaken over time based on how they're used.
Okay, that makes sense. So learning something new strengthens certain connections in your brain.
Exactly. And memristors, they kind of behave like that too. They can have this range of resistance states, so they're not just on or off, they can be somewhere in between. And the really cool part is that their resistance can change based on the electrical current that's passed through them, so you can sort of train them like you can train a neural network.
Okay, so it's like they have a memory of past electrical activity.
Exactly. That's where the name memristor comes from. It's a resistor with memory, and that memory is key to mimicking the way brain cells learn and adapt. But as with any new technology, there have been some significant hurdles to overcome to make memristors practical.
Yeah, from what I've read, the older versions of memristors weren't exactly ready for prime time, right? Like there were issues with them being unreliable or needing very specific power settings or something.
Right, they were kind of finicky. You know, the materials they were made of could degrade over time, or they were sensitive to changes in temperature, and their functionality was somewhat limited, not very practical for widespread use.
But these new memristors, the ones this research is focused on, they seem to be addressing some of these problems, right?
Exactly. And what's really significant here is not just an incremental improvement, but a fundamental shift in how these memristors actually work.
Okay, so what's different about these new ones?
So this research highlights this brand new electrochemical mechanism. Think of it this way. Instead of relying on a fixed material property that could degrade or be sensitive to external conditions like temperature, these new devices use the controlled movement of charged particles.
Okay, slow down for a second. Controlled movement of charged particles. It sounds complicated.
It is, but think of it like a tiny rechargeable battery element almost.
Okay, like a really, really small battery.
Yes, exactly. And so instead of just flipping a switch on or off, these charged particles move around within the device to store and process information. And this leads to much greater stability, both chemically and electrically.
So it's not just about being more reliable, it's about being more versatile too.
Absolutely. The chemical process allows for much more fine-grained control and expands what they can do. And on top of that, it actually simplifies the overall complexity of building computer systems with these new memristors.
So it's a win-win.
In a lot of ways, yes. So we've got these more stable, more versatile components that could be the foundation for a whole new generation of AI hardware.
Okay, so let's connect this back to AI. You mentioned this idea of catastrophic forgetting earlier. Can you explain what that is and how these new memristors might help address it?
Right. So catastrophic forgetting is a major bottleneck in a lot of current AI systems, especially artificial neural networks. Basically, it means that when you train an AI on a new task, it can completely forget how to do the tasks it learned previously. It's as if learning to ride a bike suddenly made you forget how to walk.
That sounds like a really big problem.
It is. It's incredibly inefficient, and it really limits the complexity of the tasks that AI can learn. But these new memristors, with their unique electrochemical properties, they offer a potential way around this.
Okay, how so?
So remember how we talked about how these new memristors aren't just limited to an on or off state. They can exist in this spectrum of states, right?
Yeah, like a dimmer switch instead of just an on-off switch.
Exactly. And that ability to control what we call the modulation, like the degree to which they allow current to flow through these different switching modes, that's what's so promising for solving catastrophic forgetting. It allows the network to encode new information without completely overwriting the old. It's more like layering new knowledge on top of what's already there.
That makes sense. So instead of just wiping the slate clean every time it learns something new, it can actually build upon its previous knowledge.
Precisely. And if we think about the potential this has for the future of AI, it's pretty exciting.
Like what kind of potential?
Well, imagine AI that can continuously learn from new data and experiences without losing its prior knowledge. AI that can adapt to changing environments, handle complex, real-world scenarios that require continuous learning.
So stuff that current AI struggles with.
Yes, exactly. We could see things like much more sophisticated robots, personalized medical treatments that evolve as new patient data comes in, AI assistants that truly learn and grow with your needs over time.
That's pretty wild to think about. So from these incredibly tiny components that could power the future of AI, we're going to shift our perspective now to the truly vast scale of the cosmos, right?
That's right. Prepare for whiplash.
Our next topic is the remarkable detection of oxygen in the most distant galaxy ever observed, known as JADES GS-Z14-0. Just saying that name is a mouthful.
I know, right? Astronomers don't always go for catchy names.
But the distance we're talking about here is just mind-boggling.
Absolutely. The light from this galaxy has been traveling for an astounding 13.4 billion years to reach our telescopes.
13.4 billion. So when we look at this galaxy, we're essentially seeing it as it was 13.4 billion years ago.
Exactly. It's like a time machine. We're seeing a snapshot of the universe as it existed just a couple 100 million years after the Big Bang.
Wow. To put that into perspective, the universe itself is estimated to be about 13.8 billion years old, right?
That's right. So we're talking about a very, very early chapter of cosmic history here. The universe was still in its infancy.
And to think that scientists can actually detect a specific element like oxygen from something that incredibly far away, it's kind of amazing.
It is remarkable. It speaks to the incredible advancements we've made in observational astronomy.
So how is this discovery even possible?
This groundbreaking observation was made using something called ALMA, the Atacama Large Millimeter Sub-Millimeter Array.
Okay, another mouthful. What is that exactly?
It's this network of incredibly sensitive radio telescopes located high in the Atacama Desert of Chile. It's one of the most powerful ground-based telescopes in the world. And what ALMA is really good at is detecting faint signals from very distant objects.
So it's like having incredibly powerful ears listening to the faintest whispers from the early universe.
That's a great analogy. And in this case, the whisper they picked up was the signature of oxygen in the light coming from this incredibly distant galaxy.
Okay, so why is the detection of oxygen so significant?
Well, astronomers classify oxygen as a heavy element, and by that we mean anything heavier than hydrogen and helium, which were the primordial elements created in the Big Bang.
So early on, the universe was basically just a giant cloud of hydrogen and helium.
Pretty much, yes. Heavier elements like oxygen, they form later through nuclear fusion inside stars, and then they're dispersed out into space when those stars die and explode as supernovae.
Okay, I see. So to find oxygen in a galaxy that young, it suggests that a significant amount of star formation and star death must have already occurred.
Exactly. It implies that at least one generation of stars must have already lived and died within this galaxy, enriching it with oxygen, all within the first few 100 million years of the universe's existence.
Wow. And that's surprising, right? Because our current understanding of the early universe suggests this process should have taken much longer.
That's exactly right. This finding challenges our existing models of how quickly galaxies formed and became chemically enriched in the early universe. We thought this process would have taken considerably longer.
So does this mean our current timeline for how the early universe evolved is wrong?
Well, it might need some adjusting. This discovery suggests that maybe galaxies can form and undergo these rapid cycles of star birth and death much faster than we previously thought, and it's prompting cosmologists to revisit their models and consider what mechanisms could drive such rapid chemical enrichment in these nascent systems.
So this isn't just some interesting data point about a faraway galaxy. It's potentially rewriting our understanding of how the universe itself came to be the way it is.
It is. It's a crucial observational constraint on our theories, and it also highlights the incredible power of these new instruments like ALMA and, of course, the James Webb Space Telescope.
Right, the James Webb Telescope, it seems like we're hearing about that all the time these days. What role does it play in all of this?
It's providing complementary data. So ALMA is great at detecting these faint signals from heavy elements, but the James Webb Telescope can see these early galaxies across a broader range of wavelengths, giving us a more complete picture.
So together they're like this powerful tag team, giving us this unprecedented glimpse into the universe's infancy.
Exactly. It's a really exciting time to be studying the early universe.
From the grandest scales of a cosmos, let's bring our focus back to Earth now. Our final topic is a fascinating study exploring the potential role of the placenta in the development of neuropsychiatric disorders, specifically schizophrenia.
Now, this is an area that I think a lot of people might not immediately connect.
Right, when I first saw this, I was like, the placenta, what does that have to do with mental health?
Right, it seems like a bit of a leap, but this is actually a relatively new and intriguing avenue of research.
So, for a long time, the focus in understanding conditions like schizophrenia has been primarily on genetic predisposition and brain development after birth, right?
That's right. The assumption has been that these conditions largely arise from a combination of genes you inherit and experiences you have after you're born.
But this study is suggesting that something might be going on even earlier during pregnancy.
Exactly. And this is where the placenta comes in. We typically think of the placenta as this organ that provides nutrients and oxygen to the developing fetus, but it's becoming increasingly clear that it plays a much more complex role.
So, how does the placenta potentially factor into the development of a condition like schizophrenia?
Well, the key findings here center around epigenetics, and specifically a process called DNA methylation that happens within the placenta.
Okay, epigenetics, that's another one of those terms that gets thrown around a lot these days. Can you remind us what that means?
Sure. So you have your genes, which are like the blueprint for your body, right? But epigenetics is like the software that controls how those genes are expressed, whether they're turned on or off or dialed up or down.
Okay, so it's not just about the genes themselves, but how they're being used.
Exactly. And one of the main ways this happens is through DNA methylation. Think of it as like chemical tags that can attach to your DNA and influence how those genes are expressed.
So like a volume knob for your genes.
Yeah, that's a good way to think about it. And what the researchers found in this study is that specific patterns of DNA methylation in placental tissue were associated with an increased risk for neuropsychiatric disorders in the child.
Okay, so are they saying that these methylation patterns are somehow causing these disorders?
Well, it's not quite a direct cause and effect relationship, but it does strongly suggest that genetic risk factors for these conditions might begin to exert their influence much earlier in development, maybe even before birth. And it's through these epigenetic mechanisms in the placenta that this might be happening.
Okay, so let me try to summarize this. They're basically saying that these epigenetic changes in the placenta could be an early warning sign that a child might be at higher risk for developing a condition like schizophrenia later on.
That's a good way to put it. It's like a clue, a piece of the puzzle that we haven't really been paying attention to before. And it really shifts our understanding of the neurodevelopmental origins of these disorders, suggesting that the foundations might be laid much earlier than we previously thought.
That's pretty huge. So if we can identify these early epigenetic markers in the placenta, what could that mean for prevention or intervention?
Well, that's the really exciting part. Understanding these early changes could open up all sorts of possibilities for identifying individuals at higher risk much earlier in life, maybe even prenatally.
So instead of waiting for symptoms to emerge, we could potentially intervene much sooner.
That's the hope. Of course, there's still a lot of research to be done, but this is a really promising avenue, and it highlights the importance of the prenatal environment and the placenta's role in shaping brain development. It could lead to new targeted interventions or personalized prevention strategies.
So potentially we could be talking about preventing these conditions altogether.
Well, it's too early to say for sure, but it's definitely a possibility that we need to explore further.
It's amazing to think that something as seemingly simple as the placenta could have such a profound impact on our mental well-being,
It is. It just shows how interconnected and complex biology is.
and how much we still don't know.
Absolutely.
Well, it's been quite a journey today, hasn't it? We've gone from the tiniest components of future technology to the vastness of the early universe, and then back to the very intimate and complex biology of our own beginnings.
It's been a whirlwind tour of the frontiers of scientific discovery.
And I think it really highlights the incredible breadth and depth of what's going on in the world of science right now.
I totally agree. It's a really exciting time to be following all of this.
And for you, our listener, I want to leave you with this thought. What if the underlying principles governing these seemingly unrelated domains are more interconnected than we currently appreciate?
That's a great question.
I mean, whether we're talking about information processing and artificial neural networks, the formation of cosmic structures through gravity, or the delicate interplay of genes and environment in the developing brain, we're essentially exploring the emergence of complexity in different forms.
Different scales, different systems, but perhaps some common threads running through it all.
Exactly. So what future insights might arise from seeing these diverse fields, not as separate silos, but as different facets of the same fundamental processes at play in the universe?
It's definitely something to ponder.
Thanks for joining us on this deep dive. It's been a pleasure exploring these ideas with you. Until next time.
Thanks for having me.